polyatomic molecules.
Thank you for the kind introduction. I would like to thank the organizers for giving me this opportunity to present my work here. I'm from Johns Hopkins University. I do not know what is your impression about AMO physics at Johns Hopkins. Probably not very much, because we do not have AMO physics in the physics department. I'm from Department of Chemistry, but this is going to change very quickly. I'm not the right person to show this, but since this is a perfect audience, so my colleague at physics actually told me to show this to you. And so Johns Hopkins is rebuilding AMO physics, and all I know is that the leadership is very determined, and this position and the position afterwards will be very strongly supported. For information, please ask the right person. Okay, so I hope you find this interesting. And so this is I'm going to show a usual procedure for laser cooling of molecules from a person who knows nothing about what is happening inside the boxes. So the three steps here. The point is that my research is mainly facilitating the second step, that is laser slowing using radioactive forces that you do many photon scatterings for molecules. And so, oops, sorry. So here, in the laser slowing step is actually a bottleneck for many molecules, because here one wants to do very rapid and closed optical cycling. So it is important to choose the right molecule for the experiment, because as you know, the laser system is molecule specific, and they are at the moment expensive. And also these are a lot of efforts to work on one molecule. So there's one key metric is that we would like to have Frank-Condon factors that are as diagonal as possible in these molecules, assuming that the Frank-Condon factors will fall off when you go to higher vibrational states. And Robert has this beautiful idea of engineering laser-coolable molecules based on local excitations in molecules, and there are many studies devoted in this direction. And there's also another important, a second important factor here, that is that we can have weak transitions that are borrowed through perturbations. So here, even if we have our molecule has a very diagonal Frank-Condon factors, the intensity borrowing mechanisms can also borrow weak transitions. So the weak vibronic transitions will be the focus of this talk, and we are going to focus on the vibration, so the vibronic transitions. And the next speaker, Jinjun, will tell us more about not only the vibronic transition, but also the rho vibrational interactions. So here, this is actually an unprecedented interest in weak transitions, because I guess in the past, in molecular spectroscopy, when we have transitions with branching ratios lower than 10 to the minus 3, we would say that, okay, that there is a weak transition there. But now, actually, whether it is 10 to the minus 3 or 10 to the minus 6, actually is a qualitative difference. And all transitions above 10 to the minus 5 will actually determine the success or failure of a laser cooling experiment in the laser slowing process. So this poses both challenge and also opportunities in molecular spectroscopy, both in measurement and also in computation. So I will use a generic kind of molecules, linear triatomic molecules as example in this presentation. So we work with metal monohydroxide we will use mu1 to mu3 to denote the metal-oxygen stretch, the bending motion, and the OH stretch. So in this notation, 1, 0, 0 would be the V equals 1, the metal-oxygen stretch. This is the V equals 1 bending mode. This is a ground state. So one thing that I would like to emphasize is that many of these cooling experiments would use a doublet pi state as the upper state, and we are interested in the transitions from the vibrational ground state of the upper electronic state to various vibrational state of the ground electronic state. So to give you an idea the kind of weak transitions that one is interested in here, I would like to show this spectrum, this spectacular measurement in Doyle's group, and I stole this from an email sent to me from Ben. And so in this beautiful spectrum, what is shown here is a typical spectrum. We have a strong transition and quite strong transition, some weak transition. So in the past, in the molecular spectroscopy study, we can stop here and say that there are some weak transitions here. And you can assign this to be the V equals 2 bending mode because we do not see the V equals 1 since that is nominally symmetry forbidden. But now, in laser cooling experiment, one is interested in the weaker transitions that are shown here. So you can see that there are a number of transitions here, including the forbidden transition. Actually, this nominally forbidden transition is the relatively strong ones in this category, and the intensity here has been multiplied by a factor of 10,000 to be shown here. So these are really weak transitions, but as the audience know better than I do, these will cause leakage that will cause problems in deep laser cooling of such molecules. So the computational challenge here is that we are now aim at, I would say in general, high accuracy, but really it is high sensitivity calculation. We need to get all the weak transitions at least correct to the order of magnitude, and this requires good representation of the potential energy surfaces for this triatomic molecule, and also for the vibrational wave function, we need accurate representation. And as I will show, the non-adiabatic coupling actually is very important. The nominally forbidden transitions borrow intensity through coupling to other electronic states. So here necessarily one has to go beyond one electronic state. And for state-of-the-art quantum chemistry calculation, it is always a challenge when one has to include more than one electronic state. So I would like to use a table to show to you the importance of the non-adiabatic effect and harmonic contribution before moving on to the technical details of these couplings. So here specifically, I'm showing the transition in calcium hydroxide molecule, and here are a list of 9 transitions that was repumped in this laser cooling experiment, beautifully done and published in this year. So these are the 9 transitions that were had to be repumped, and these are the branching ratios in percentage. So we can see that many of them are at the level of 10 to the minus 3 and 10 to the minus 4. So if one does a harmonic approximation to both upper and lower electronic state, this is what you get. So harmonic approximation really can get the 0-0 transition very well, and for the V equals 1 stretching mode, it is also very well, and it falls down a little bit too quickly for the bending mode, and also in general, harmonic approximation has intensities that fall down too quickly for higher vibrational state. So the bottom line here is that in harmonic approximation, one would get 3 transitions that one has to repump, but actually there are 9 here in the actual experiment. If one includes the anharmonic contribution, one actually gets improved descriptions for these allowed transitions with a higher vibrational quantum number. But there are forbidden transitions that would not show up as long as we stay in stay within one electronic state. And so here the non-adiabatic effect is important and has to be included to capture the nominally forbidden transitions. So this is the general kind of motivation that one has to include these effects into account for calculation that is sensitive enough to facilitate laser cooling experiment. But I would like to say that the harmonic approximation or one-state calculation are very valuable in providing important information for the diagonality of the Frank-Condon factors. So this, in general, is a huge battle on details, but these are the important details that one need to study this topic. And in a way, electronic structure theory, quantum chemistry, basically is a detail from the physics point of view, because the framework had been laid out by Schrödinger and Dirac many years ago. So one can say that the whole field is try to solve Schrödinger equation and the Dirac equation, and there's no fundamental. There's in this way a battle on details. So I think this is a matter of temperament that we probably are trained to be able to try to make some contribution to these calculations. So here. The non-adiabatic effects are due to the small perturbations in the upper electronic state. We learn all these interactions from Barfield's classic book about perturbations in diatomic molecules. This is a triatomic molecule, but it is a linear triatomic molecule. So the perturbations relevant here are the Ranatella coupling within the degenerate A state, and basically second order second order non-adiabatic coupling between the degenerate A state, and then there is a direct vibronic coupling between A and B state. We denote here as linear vibronic coupling, and then but within the A state there is a spin orbit coupling that leads to the splitting of the A state, and then there is a spin orbit coupling between A and B state. So the coupling between A and B state enables the forbidden transition to V equals odd number of the bending mode. Okay, so there are quite a few mechanisms that one can look in more detail. So these are this is a state that we do the main optical cycling with the ground state, and some of these states can be used in the repumping scheme. So here we will focus on the intensity borrowing for the vibrational ground state of the pi half state. So there is a vibronic coupling between A and B. This I call here direct vibronic coupling. Is a simple name. I was told that the educated name is Herzberg-Teller interaction, Herzberg-Teller coupling. But in that occasion, then I was asked, I was given a picture of Herzberg and Teller and asked who is Herzberg and who was Teller, and I was a bit illiterate in that. So the intensity borrowing here, this is actually not the intensity, but should be the transition dipole moment. So it depends on the coupling, dipole transition dipole moment between the B and X state, and then the linear vibronic coupling between the A and B state, and then the energy difference between them. So this is first order mixing in the wave function. Then, through spin-orbit coupling, there is a second-order mixing algorithm. I would call it spin-orbit vibronic coupling. So this will involve the vibronic coupling between A and B, and the spin-orbit coupling also between A and B. And here, there is an interesting denominator here that has the spin-orbit coupling within A. This is very important because it can offset the spin-orbit coupling between A and B state. So even for heavy elements, these two will grow simultaneously. So in the end, direct linear coupling will still dominate even for heavy elements. So eventually, the reason that we have the nominally forbidden transition is that the wave function for this state will actually mix in the v=1 bending mode of the B state and the v=1 bending mode of the pi3½ state. And these two can make transition to v=1 bending mode of the ground state. There is a contribution from the from Condon approximation. So we can have the derivatives of the transition dipole moment, and this breaks the symmetry. So this can also contribute to the transition into the forbidden transitions. And we will come back to this a little bit later. So for the calculation, the computational framework, this is the excellent work of Chaojun Zhang, who is among the audience, who did all the programming work and did all the calculations and analysis. So basically, our computational framework is to use a multi-state quasi-diabatic Hamiltonian, and this was developed very early in Heidelberg, and sometimes people, and including myself, refer to this as KDC multi-state Hamiltonian. And John Stanton has been using this Hamiltonian with very highly accurate parameterization for quantitative calculations of molecular spectroscopy. This is a very nice review that John recently wrote with Terry Miller and his postdoc, and I would highly recommend this. And for the parameterization of the Hamiltonian, we use the equation of motion couple cluster theory that you heard about in the morning. Because the point is that in these calculations, we care about the accuracy of the local potential angular surface. So around the equilibrium structure, if you break the bond, of course, one has to use multi-reference methodologies. But for the local potential angular surface, couple cluster theory provide accurate measurement, accurate calculations. And also we calculate the coupling parameters. The diabatic coupling parameter, we follow the recipe by John Stanton and Jürgen Gauss and Takatoshi Ichino within couple cluster theory, and Chaojun had contributed to the calculations of the spin orbit matrix element. And for the vibrational wave function, we did variational calculations using discrete variable representation. And so here, Chaojun's implementation used the algorithm outlined by Bill Miller in early 90s, and normal coordinate representation, and for internal coordinate representation, Brian Shangala has a very powerful program called Nitrogen that can do multi-state quasi-diabatic calculations. I think this paper was when Brian was an undergraduate student in Bob Field's group at MIT, and Brian is in the first floor of this building. Here Chaojun wrote his own program within C4 using the Miller algorithm, and we will be focusing on the vibronic transitions. And so very quickly, the construction of the quasi-diabatic Hamiltonian start with the adiabatic representation. Then one do the diabatic transformation from the adiabatic to quasi-diabatic representation. This gives us an off-diagonal Ranatella matrix element. Then that gives us the A state. Now we add the B state. The coupling between A and B without spin is the linear vibronic coupling. They go in this block. So this matrix starts growing, and from 1 state to 2 state, now, yes, thank you. Now it is, including B, it is 3 state. Then with spin orbit coupling, it becomes a 6 state Hamiltonian because we have the alpha block and the beta block. And the spin orbit coupling comes in the off-diagonal block when we use the pi x and pi y representation. So the numbers, these are the treatment of electron correlation, couple cluster singles and doubles, couple cluster singles, doubles, and triples. So it is a systematic improvement, but the point is that it is not changing very much. So couple cluster singles and doubles actually are pretty good. This is to change from triple zeta basis set to quadruple zeta basis set. So just to show you that how the results would change, and we have an idea how accurate the calculations are because these are systematic improvement. In the end, these are the best theoretical calculation. These are the measurement for energy levels. If we give the difference, the typical error is a few several to 10 wave number. This is a typical accuracy that one gets in the calculation of infrared spectrum, for example. This is by no means high accuracy in terms of high accuracy laser spectroscopy, but it gives a reliable description of the vibrational states here. So the branching ratios, these are the harmonic calculation. This is a KDC multi-state DVR calculation. And we are changing the surfaces. It doesn't change very much. So I think the important thing is just to say that these results do not change too much. And our calculations compare favorably with the measurement, at least in terms of the order of magnitude. So will be fun to show this. So now, sorry, these ones in red are the strong transitions. And this is for ytterbium hydroxide. And one gets this not in high accuracy. I think most of the remaining errors are due to the structure of the molecule. It is not perfect, but the sensitivity, but order of magnitude, they are okay. And for weak transitions, I think there are reasonable agreement here. There are 2 very small transitions that were identified from the experiment but didn't show up in the calculation. So there are more to continue to check for the accuracy of the calculation. These are very small transitions seen in the experiment. So overall, one have tools to give reasonable sensitivity in the calculations that can capture the weak transitions, and one can do something with it with this. And just one slide to say that the perturbation theory in the borrowing mechanisms work pretty well. So the perturbation theory and the DVR compare favorably. When we go to the heavier elements, this ratio between direct vibronic and spin orbit vibronic is still in favor of direct vibronic coupling. So that is the main mechanism. I haven't shown results for transition dipole derivatives, but since we are working with a diabatic representation in which the wave function changes very slowly, so the numerical results show that this is insignificant. It does not contribute very much. But in adiabatic representation, this will have large contribution. I will flash 2 slides for the wonderful work that Zach Lasna has done for strontium hydroxide, and I refer you to his talk tomorrow morning. And here the calculations facilitate his study of this molecule to come up with a laser cooling scheme for the strontium hydroxide molecule. which has a strong motivation to study for the search of new physics. And I would like to present one prediction. And I am a relativistic quantum chemist by training, so going to heavy elements is the way to go. It is not that favorable for laser cooling because it is very heavy, but but it has good sensitivity for beyond standard model physics. That is a good thing. So there are significant recent progress in fluoride, iridium fluoride, and here is the cation cationic molecular cations containing iridiums, a major progress in experiment. And there are wonderful studies that propose these molecules and molecular cations for laser cooling. And of course, the motivation is that iridium is sensitive to multiple sources of time reversal violating interactions. So we are going to show quickly the result for radium hydroxide. So here, interesting thing is that spin-orbit coupling actually comes in now, and it changes the differences between the bond lengths of the upper state and the lower state actually favorably. So without spin-orbit coupling, this is a bond length difference. With spin-orbit coupling, it is halved. This means that it actually makes the from quantum factor more diagonal. Yes, but the interesting thing is that the intensity borrowing mechanism through direct vibronic coupling is quenched. So here the intensity for the V equals 1 bending mode is only 10 to the minus 5, much smaller than in calcium hydroxide. In this calculation, then the diabatic coupling constant is of importance. And here we are doing a scalar relativistic calculation. So what we plan to do next is to implement a calculation for diabatic coupling constant with spin-orbit coupling and see how that would change this parameter. But overall, these are all the transitions beyond 10 to the minus 5. So relatively fewer transitions is needed for this molecule to scatter many photons, but it is heavy. So the true experts will hopefully will figure out how many photons we would needed. So we need to look at whether there is a dark state, because for barium hydroxide, there is a dark state, a delta state below the pi state. So here we use a calculation for radium fluoride to benchmark our calculation, and here we compare with high-quality calculations in the literature. It's pretty good. I only show two numbers here, just to show that the delta state is above the pi state. So there is no dark state here. In summary, we focus on vibronic branching ratios for linear polyatomic molecules, and we would like to look into nonlinear molecules and also to go to spinor representation with spin-orbit coupling for the coupling parameters for heavier molecules. And the perturbation theory formulation might be useful for studying these effects in larger molecules. And with this, I would like to thank many great collaborations from the AMO physics community for the work I present here. Many thanks goes into John Doyle's group, the collaborators and friends there for their wonderful work together. For the work on radium hydroxide, I would like to thank Nick Hassler and his group for continued encouragement and also many valuable discussions. And I would like to thank you all for your attention. Yes.
One is the doublet sigma state is a plus, not a minus state.
Oh, yeah.
The second is that lambda doubling is going to enter into these intensities in in an explicit way, which I'm not sure you talked about.
No, I haven't.
And third is that ytterbium
Yeah.
has a problem because the F-13
Yes.
configurations mess things up tremendously.
Yes.
And that's only recently been realized,
Yes.
and it's going to make the vibronic coupling calculations really complicated in ytterbium.
Yes. So for lambda doubling, we haven't considered that. And in a general response in improving the calculations. So one direction is to do a full row vibrational calculation instead of a vibronic calculation. So actually slipped into Brian's office on the first day of the meeting. Yeah,
Really,
yeah.
the pi
So,
state is actually 4 states.
yeah, yeah.
And so the Frank-Conan factors for each of the 4
Yes.
components will be important, different.
Yes, yes. And the F-13 states, yes, we have actually calculated the positions for those F-13 -1 states as well. The detection for that is very challenging because the range of the transition energy is also a challenge in that.
Many things to tell you about.
But yeah, maybe it's best to now think again.
I have a minus one question.
Oh, sure.
If you could go to one of, discuss the spin orbit in one of those diagrams, slides would do. Yeah, even here.
Okay.
So when you refer to the spin orbit coupling between sigma and pi or pi and pi,
Yeah.
are you referring to a higher order spin orbit coupling? Because where is the spin orbit coupling when you go from sigma, between sigma and pi?
Yeah, the spin orbit coupling from between A and B state, for example, sigma and pi, those you can understood in the spin diabatic representation. That is the higher order spin orbit. It is, yeah, it is.
The usual spin orbit coupling, because it looks like orbit-orbit coupling.
So the coupling within the pi state is induce a splitting, but the coupling between A and B is is a common, yes.